This short series of lectures is intended to answer one question and one question only. Does the perturbation series that we use in quantum mechanics converge? And as a follow-up, if it does not, then is it of any use? Now, I have already discussed perturbation theory in quite great detail in earlier lectures as part of my advanced quantum mechanics course. Let me just remind you of the very basics of the method that we use there. We deal with a Hamiltonian H which depends on a parameter lambda in the following manner. The Hamiltonian splits into two pieces, H0, a Hamiltonian for which we know the exact solution, plus a perturbation term which is parameterized by this parameter lambda. We write that as lambda H prime. And what we are of course looking for are the energy eigenfunctions and eigenvalues of this H of lambda. These will of course depend on lambda. So these are really psi I of lambda, and the energy has already been indicated here. Depend on lambda, so do the energy eigenfunctions. And what we then do is write epsilon I lambda, the ith energy eigenvalues, as a series, a power series in lambda with the coefficients epsilon I 0, that's the 0th order term, then epsilon I is 1th order term, 2th order term, and so on. Similarly, we also expand the eigenket psi I lambda in a series of eigenkets in powers of lambda. The next step is simply to plug this in the equation hi lambda psi I lambda is epsilon I lambda psi I lambda, and once I do that, I get a rather complicated looking equation. What makes my life easy after that is that I can take these terms order by order in powers of lambda on both sides, and get a series of equations which gives us the various coefficients that we are looking for. Now, all this would have been fine if this perturbation series had been a convergent one, and then all of these manipulations that we do in order to arrive at these equations would actually be consistent. For many interesting quantum systems, however, the perturbation series does not converge. For example, if you take a look at a very, very standard example of a perturbation series, the so-called quartic oscillator, where in addition to the harmonic oscillator term H0, which is exactly solvable, you have a perturbation term given by x to the 4. I have written lambda x to the 4 here, but this lambda is really in front of the H prime. So H0 plus lambda H prime is my full Hamiltonian. If I carry out the calculation for perturbation theory for this particular interaction, we are going to get a series of terms. But unfortunately, the radius of convergence of the perturbation series here is strictly 0. So this series is going to diverge for any non-zero value of lambda. Why do we know that? The answer is pretty simple actually. The answer lies on the basic properties of a powered series. If it converges on a disk centered at the center of the series. In this case, lambda equal to 0. So if the series that we are writing down here, series in powers of lambda, converges for any positive lambda, then it would have to converge for minus lambda as well, because lambda and minus lambda would both be inside the same disk, centered at the origin. So, if your series did converge for a positive value of lambda, it would also have to converge for a negative value. But for a negative value of lambda, the Hamiltonian, p square by twice m plus half m omega square plus lambda x to the 4, cannot have any bound state, because the lambda x to the 4 term in the potential makes the potential drop out to minus infinity for a negative lambda for large enough x. But if the series had converged for positive lambda, it would have predicted an energy eigenstate also for negative lambda, which is impossible. A direct calculation of the perturbation series, which can be done using advanced techniques for this particular problem, bears out the result that we have stated here, that the radius of convergence of this perturbation series is strictly 0, which means the only value of lambda for which the perturbation series actually converges is lambda equal to 0. Now, if you have not met this result before, this could come as a bit of a disconcerting piece of news. If the series does not converge at all, what is the justification for this term-by-term matching process by which we arrived at the coefficients in the first place? The answer to that, which is given, is the following. The series is actually not convergent in general, but is asymptotic. And as a result, the first few terms often provide a good approximation to the final answer. Now, this actually perhaps raises more questions than it answers. The first question that should be asked, given the fact that asymptotic series are not really part of standard mathematical training, at least in elementary level physics courses, is what exactly is an asymptotic series? And secondly, how do we know that the perturbation series that we get using this procedure is actually asymptotic? And finally, how does the fact that the series is asymptotic tell us that the first few terms of the series should be good enough to give me a good estimate of the actual value? We will try to answer these questions in this lecture, or maybe a series of lectures, because this is a really large topic. I will first try to talk about what asymptotic series are, talk of a few examples which will hopefully make the ideas clear, and then go on to show why the perturbation series that we derive in quantum mechanics is actually an asymptotic series, and also in the process justify the fact that the first few terms of an asymptotic series may be good enough for the purpose that we have. First, let us talk about asymptotic series. Before we talk about that though, we need to understand the adjective asymptotic. What does it exactly mean in mathematics? Now, before we go to the precise definition, let me just assure you that asymptotics is not that novel a concept. We actually use the idea of asymptotics all the time. For example, sin x is asymptotic to x when x is small. That's something which we have used often enough, especially say when we talked about the simple pendulum equation being an approximately simple harmonic equation by replacing a sin theta there with theta. A slightly less familiar example would be the fact that e to the x plus x is actually asymptotic to e to the x as x goes to infinity. In other words, we do accept the fact that e to the x plus x and e to the x are two different functions. And the difference, by the way, does not go to 0 as x goes to infinity. The difference, x, actually diverges as x goes to infinity. Yet, in a sense, these two functions are pretty close to each other. In other words, adding an x to e to the x does not really make any difference once x is large enough. Something even simpler, square root of x is asymptotic to 2. Not the number 2 really, but the constant function 2. As x goes to 4, that sort of should be obvious. And finally, a formula that we have all used from time to time, the so-called Stirling's formula for log of n factorial. Log n factorial is n log n minus n, as n becomes very, very large. That also is an asymptotic expression. So asymptotics in a sense tells us that two functions are close to each other, but not in the sense that the difference necessarily vanishes, as you can see from the example of these two functions. So now let us make this notion more precise. For this, I am going to use the notation and definition specified in a textbook, a very nice textbook on this subject. It's a textbook by Bender and Orszag, and its name is Advanced Mathematical Methods for perhaps scientists and engineers. I don't exactly recall the name, but if you search Bender and Orszag, I'm pretty sure you're going to land up with this book. Now, the definitions that we have to put in place before we understand asymptotics formally are the following. First, a notion of negligible. F of x is negligible compared to g of x. This double less than sign stands for negligible as x goes to x0. What do we mean by this? What we mean is if you take the ratio f of x by g of x, then in the limit x goes to x0, this ratio vanishes. That is what I mean when I say f of x is negligible compared to g of x as x goes to x0. So x square and x, both of them tend to 0 as x goes to 0, but x square is negligible compared to x as x goes to x0, simply because the ratio x square by x in the limit x goes to 0 vanishes. In fact, if you compare any two powers of x, the higher power is negligible in comparison with the lower power as x goes to 0. On the other hand, as x goes to infinity, it's the lower power which is negligible compared to the higher power. Okay, the notion that of negligibility, or this being much less than, is handy in defining the notion of asymptotics. You say two functions f of x and g of x are asymptotic to each other as x goes to x0 if the difference between the two, fx minus gx or gx minus fx, it doesn't really matter which one, is negligible compared to g of x as x goes to x0. So you say two functions are asymptotic if their difference is negligible with respect to any one of them. You could have used g of x on the left hand side here or f of x. You should be able to convince yourselves that would make no difference to the final result. Asymptotic essentially means the difference is not necessarily 0, but is negligible compared to their size. If you look at e to the x plus x and e to the x, you can easily see that the difference x does not vanish as x goes to infinity. In fact, it blows up as x goes to infinity, but is actually negligible compared to e to the x, which is why the two functions are actually asymptotic to each other. Well, if you use the definition of negligible properly, you see that the limit as x goes to x0 of this ratio fx minus gx over gx is actually 0, which tells you that the limit of fx by gx as x goes to x0 has to be 1. So fx and gx are close to each other, but not necessarily in the sense of difference, but actually in the sense of ratio. As x goes to x0, the ratio of these two functions goes to 1. Okay, let's check this out for some specific cases. Well, I've been using this example over and over again. If you call this f of x and this g of x, and you're claiming that they're asymptotic as x goes to infinity, the proof of that can be figured out in several ways. In fact, I've already explained why that's the case, but still, if you look at this equation, limit as x goes to infinity e to the x plus x by e to the x is limit as x goes to infinity of 1, which comes from this division, plus x e to the minus x. As you all know, this thing goes to 0 in the limit x goes to infinity. So this final limit is 1. So fx and gx in this case has a ratio whose limit as x goes to infinity is 1. So fx and gx are asymptotic to each other as x goes to infinity. As I have already said before, the difference between fx and gx here actually diverges as x goes to infinity. So two functions being asymptotically close does not mean that they become close in the sense of difference vanishing. Okay, another example of asymptotics. Sin x and x. If you look at the difference between them as x goes to 0 in this case, sin x minus x divided by x. As you all know, sin x has a power series which goes x minus x cubed by 3 factorial plus x to the 5 by 5 factorial and so on. So using that, we can easily see that this limit is 0 as x goes to 0. If you don't like using the infinite series here, you can also use L'Hopital's theorem, which tells you that this has the same limit as cos x minus 1 by 1. Limit as x goes to 0 of sin x minus x by x has to be this. And that, as you can easily check, is 0. So we have justified something we all knew from childhood, that sin x is asymptotic to x as x goes to 0. Maybe we did not know that in this language, but at least in high school we have definitely learned that when x is very small, sin x and x are in a sense close to each other. And that's what asymptotics is capturing for us. One important point that we need to make is, because you have to divide by g of x to say that something, the difference is negligible compared to g of x cannot be identically 0. And therefore, saying that a function f of x is asymptotic to 0 as x goes to 0 is plain wrong. Unless f of x is identically 0, in which case it's trivially asymptotic to 0. So if you leave that one case out, you should never be able to say that some function is asymptotic to 0. You can compare two functions and say whether they are asymptotic to each other, but not if one of these functions is identically 0. So that's just a warning. And sometimes we have to be careful about this when we do various manipulations involving asymptotic functions. So, although x does vanish as x goes to 0, it would be wrong to say x is asymptotic to 0 as x goes to 0. Now we come to the important notion that we are really interested in, the notion of asymptotic series. Now, let's look at sin x again. We already know that sin x is asymptotic to x as x goes to 0. Is it asymptotic to x plus x square? The answer, of course, is yes. If you take the ratio of sin x to x plus x square as x goes to 0, do I get 1? The answer is, of course, I do. Sin x by x into 1 by 1 plus x, that's what this ratio really is. And limit as x goes to 0 of this is limit of sin x by x as x goes to 0 times the limit of 1 by 1 plus x as x goes to 0. And that, of course, is exactly equal to 1. So sin x is asymptotic to x plus x square. In fact, not only is sin x asymptotic to x plus x square as x goes to 0, it's very easy to see that sin x is asymptotic to any of these infinitely many possible series, alpha x plus beta x square plus gamma x cube plus delta x to 4 and so on, as long as alpha is equal to 1. Beta, gamma, delta, all these coefficients can be completely arbitrary. Now that is not what we mean by an asymptotic series. A series which is asymptotic to the function as x goes to x0 is not what we are looking for, because there are infinitely many such series that we can write down. What we are really looking for here is a much more precise notion. And now let me define what that is. A power series an x minus x0 to the power n, with n running from 0 to infinity summed over, is said to be asymptotic to the function f of x as x goes to x0, and you write that with the tilde notation, f of x is asymptotic to this power series as x goes to x0 if for every integer, positive integer, capital N, the following holds. The partial sum up to capital N from small n equals 0 to capital N of this series is actually very, very close to f of x, in the sense that the difference between f of x and the partial sum has to be negligible 2x minus x0 raised to the power capital N. So at every value of capital N, the difference between fx and the partial sum up to n terms is negligible compared to the last term which you are keeping. Here, when I say last term which you are keeping, I mean just the power of x minus x0. Forget the coefficient. This is how you define a power series to be asymptotic to a function. And if you follow this, you will find that this is a very, very precise definition which allows us to pinpoint what these coefficients a and are. We are going to see that soon. An equivalent way of stating asymptotic power series is the following. This difference between f of x and the nth partial sum must be asymptotic to am x minus x0 to the power m, where m is the next non-zero coefficient, where am actually is the next non-zero coefficient of the series. So after capital N, it might so happen that the capital N plus 1th, capital N plus 2th, etc. terms are all 0, but capital M is the next non-zero coefficient. At every stage, if you take away the partial sum up to that particular power, from f of x, the difference has to be asymptotic to the next non-zero term in the series. In other words, at any given stage, the function is as close up to the particular power you are dealing with as possible. The difference only is in a higher power. So let's try to figure out what the asymptotic series will be for sin x. We will do this the long way by just relying on the definition. So this means that all the individual partial sums, like partial sum up to capital N equal to 1 is just alpha x, that has to be negligible compared to x. So sin x minus alpha x must be negligible compared to x as x goes to 0. Which in other words means sin x minus alpha x by x, this ratio has to go to the limit of 0 when x goes to 0. But this of course is easy to figure out. This is just sin x by x's limit minus alpha. If that is 0, it tells you that alpha has to be 1. Something we already knew. What about beta? Well, sin x minus beta x squared, that is, you have taken these two terms where we have already used the fact that alpha is known, it's 1. This difference must be negligible compared to the power that we are keeping, the highest power, x squared here. So that tells us that this ratio, sin x minus beta x squared over x squared, must vanish in the limit x goes to 0. And a pretty straightforward calculation will tell you that this must lead to beta equals the limit as x goes to 0 of sin x minus x by x squared. And this is something which is pretty easy to figure out. Answer here is simply 0. So beta is 0. There is no quadratic term in the asymptotic series. What about n equals 3? Well, if you include the n equal to 3 term, then the series is x, 1 times x plus 0 times x squared plus gamma x cubed. So you're taking that away from sin x. You're claiming that this has to be negligible compared to x cubed. So this is the limit which has to vanish. And that immediately tells me that gamma has to be the limit as x goes to 0 of sin x minus x by x cubed. You take the limit of this. Further, you can calculate this just by using L'Hopital theorem. So sin x minus x differentiates to cos x minus 1. X cubed differentiates to 3x squared. This still is of the form 0 by 0. So you differentiate numerator and denominator once again. You get minus sin x by 6x. And I can either use L'Hopital once again or just realize that sin x by x has 1 as a limit. So this limit is minus 1 by 6. So up to the cubic term, the asymptotic series for sin x is x minus x cubed by 6. At this point, it should be rather obvious that what we are actually doing here is recovering the infinite series for sin x. Of course, the infinite Taylor series, which is actually convergent in the case of sin x. What we do get is that the asymptotic series that we have defined here is nothing but the Taylor series, at least as far as sin x is concerned. In fact, you will see that there is a deep connection between asymptotic series on the one hand and Taylor series on the other. Indeed, if we start with a general function y of x and we claim that it is asymptotic to this power series an x minus x0 to the power n as x goes to x0, we can use exactly the same procedure that we followed earlier for sin x to figure out what the different coefficients a0, a1, a2, a3, etc. are going to be. For a0, of course, you take capital N equals 0. So the partial sum up to 0 terms, to the 0th term really, is just a0. So what we are claiming as yx minus a0 must be negligible compared to the power of x minus x0, which accompanies a0, which in this case is just x minus x0 to the power 0, that is 1. And this by definition, of course, tells you that limit as x goes to x0, yx minus a0 by 1 is 0. So a0 must be nothing but the value of y at x0 if the value exists. If the value doesn't exist, but the limit does, a0 is just the limit of y as x goes to x0. Now, what about n equal to 1? For this, we have to take our partial sum up to the 1th term, which is actually the second term of the series. So yx minus a0 minus a1 x minus x0 must be negligible, this time compared to the power x minus x0. As x goes to x0, of course. Now, this translates to the limit of x going to x0 of this difference divided by x minus x0 being equal to 0. And this immediately tells me how to calculate a1. a1 is simply going to be the limit as x goes to x0 of yx minus a0 by x minus x0. And since a0 is y of x0, then we have to have a1 as a limit as x goes to x0 of yx minus yx0 by x minus x0. Note that for this step to work, y of x0 actually has to exist. So, y has to exist at x equal to x0 if you want to find out the second term of an asymptotic series, or the second term of the asymptotic series has to exist. And that is not all. This particular limit has to exist, but we do recognize what this limit is. It's nothing but the derivative of y with respect to x at the point x equal to x0. This derivative has to exist for a1 to make sense. What about n equal to 2? Well, yx minus a0 minus a1x minus x0 minus a2x minus x0 whole square. This must be negligible compared to x minus x0 whole square as x goes to x0. Following the same procedure as before, it's easy to see that a2 is nothing but the limit as x goes to x0 of the difference between this part divided by x minus x0 whole square. Of course, what we have done is already put in the value of a0, which we know is y of x0, and the value of a1, which we know is the derivative, dy dx at x equal to x0, times x minus x0, as is there in the series. Now, one quick, easy way of evaluating this particular limit is using L'Hopital's theorem, because if you do that, you immediately get that this ratio, which is of course of the form 0 by 0 as x approaches x0, is nothing but dy dx at x minus, this term vanishes on differentiation, minus dy dx at x equal to x0 with this yielding a 1. That's the derivative of the numerator divided by 2x minus x0. And now you can easily see that this is nothing but the rate at which dy dx changes, apart from the factor of 2 that is, as x approaches x0. So this is half of d2y dx2 at x equal to x0. Proceeding further, A3, well, you know the drill by now. Limit x goes to x0 of yx minus yx0, something I forgot to write here, minus dy dx at x equal to x0, x minus x0 minus half d2y dx2 at x0. This is now, of course, A2, x minus x0 whole square. This thing divided by x minus x0 whole cube will give you the value of A3 in the limit x goes to x0. And now you can simply use L'Hopital once again. Differentiate the numerator and the denominator, you get dy dx from this, minus dy dx at x0 from this term. This term, of course, drops off. Minus d2y dx2 at x0 times x minus x0 from this factor, the half and the 2 coming from the derivative cancelling. Denominator gives you 3 into x minus x0 whole square. This is still of the form 0 by 0 as x approaches x0. So you apply L'Hopital once again. The denominator now becomes 3 factorial times x minus x0. And in the numerator, you get d2y dx2 from this. This goes away. Minus d2y dx2 at x equal to x0 from this. So the change in the second derivative from x0 to x divided by x minus x0 with a 1 by 3 factorial. So this is 1 by 3 factorial, third derivative at x equal to x0. It should be pretty obvious that proceeding in this way, the general result will be that the nth coefficient of the asymptotic series an must be 1 by n factorial dny dxn at x equal to x0, which of course is the same as the Taylor series coefficients. Note that this result works irrespective of whether the Taylor series converges or not. The infinite Taylor series may or may not converge, but as long as there is an asymptotic power series which matches the function y of x asymptotically, you are going to get the same coefficients as you would for the Taylor series. Conversely, if all the derivatives of a function g of x exist at x equal to x0, then you can use Taylor's theorem to get the following result. Taylor's theorem, by the way, is nothing but extended mean value theorem. It says that there must exist some point xi between x and x0 such that the difference between jx and the Taylor series up to p terms is given by x minus x0 to the power p plus 1 by p plus 1 factorial multiplied by the value of the p plus 1th derivative of g at the point xi. Remember, the mean value theorem essentially says that g of x minus g of x0 by x minus x0, the slope of the curve of g of x versus x, or rather the slope of the chord of the curve between the points x0 and the point x, matches the value of the derivative somewhere in between. So there is a point xi between x and x0 where g prime xi exactly matches this. This is the mean value theorem. From elementary calculus, extending this to higher and higher orders, we end up with this result, that the Taylor series actually matches g of x up to a remainder term, and the remainder term essentially is x minus x0 to the power p plus 1 by p plus 1 factorial multiplied by this p factor, which is the p plus 1 derivative of g at the point xi somewhere between x and x0. Such a point xi exists. Of course, given that all the derivatives that you have to use to calculate the Taylor series as well as this p plus 1th derivative exists. So if you now have a situation where all the derivatives of g of x exist at x equal to x0, then we can consider the infinite Taylor series some of gn x0 by n factorial into x minus x0 to the power n, summed over from n going from 0 all the way up to infinity. This, of course, is our familiar Taylor series. Can easily see that for all p, the difference between gx and the partial sum up to p terms, which is what you really need to worry about when you want to check whether this series is asymptotic to g of x or not, is given by this remainder term, x minus x0 to the power p plus 1 by p plus 1 factorial times this derivative g of p plus 1 at psi. And now, this is easily seen to be negligible compared to the last term that you are keeping here, that is x minus x0 to the power p, simply by dividing this by x minus x0 to the power p, dividing this difference, in other words, dividing this quantity by x minus x0 to the power p, and taking the limit as x goes to x0. As long as g of p plus 1 at psi is finite, that is, the function is differentiable at p0 and in some neighborhood around p0, so this derivative exists, this limit is easily seen to be 0. And hence, the difference between the pth partial sum and the function is negligible compared to x minus x0 to the power p, and this holds for all p, provided all the derivatives exist. And so the Taylor series that we wrote down is actually asymptotic to g of x as x goes to x0. Note that in all of this, we are not really using the statement that the Taylor series converges. So these partial sums, they closely approximate g of x in this particular sense, but you do not necessarily have to guarantee that the sequence of partial sums actually converges to a limit for any x other than x0, that is. So the upshot of all this is, if all derivatives of a function exist, then the function is asymptotic to its Taylor series even if the latter diverges. And this, along with what we have done earlier, tells us that the asymptotic series for a function, the asymptotic power series centered at a particular point x0, if it exists, is unique, because all the coefficients can be uniquely determined in terms of the higher and higher order derivatives of the function evaluated at x0. Okay, so we all realize that asymptotic series are not really very, very strange. They are, in a sense, very much akin to the Taylor series that we all know and love, at least for functions which are differentiable arbitrary number of times at a point x equal to x0. With the big difference that the Taylor series may not even converge, yet it would be asymptotic to the function. But this non-convergence is what raises an issue. If the asymptotic series does not converge, is it of any use? To see that, let's turn to a particular example. I've taken this example from the book by Bender and Orszag. It considers a particular differential equation. At this stage, there is just a differential equation which we want to solve. The differential equation is x square y double prime plus 1 plus 3x y prime plus y equals 0. If you write it out in the standard form, this becomes y double prime plus 1 plus 3x by x square y prime plus y by x square equals 0. So matching with the standard form, y double prime plus p of x y prime plus y times q of x, we see that p of x is 1 plus 3x by x square and q of x is 1 over x square. Now we run into trouble. We know from the fact that these coefficients blow up at x equal to 0 that this equation has a singular point at x equal to 0. But what's worse is that while q of x only has a second order pole at x equal to 0, p of x actually also has a second order pole and not a first order pole at x equal to 0. If you remember your theory of differential equations, you would realize that p of x having at most a first order pole and q of x having at most a second order pole is the criterion for the point to be a regular singular point. A point where a Frobenius-like solution exists. Not only that, where both independent solutions of this second order differential equation can be written down in the form which is free of essential singularities. That is, a form which is consistent with Frobenius method. But here what we see is x equal to 0 is an irregular singular point. Because p of x has a second order pole at x equal to 0. Now that would be rather daunting, but let's just press ahead and try to use Frobenius method anyway. After all, if you plug in the power series or an extended power series, the kind of thing that we do in Frobenius, and manage to get a solution, the fact that this point is an irregular singular point would really be moot then. What we are guaranteed is that we will not get two independent Frobenius-like solutions, but at least we might be able to get one. So let's try. The extended Frobenius power series is a power series with an additional x to the s stuck in, where s could be negative or fractional or even complex, the so-called index. Now you all know how you actually use a solution like this. At least I'm assuming you have studied this in your first year or second year mathematical physics class. What you do is y being this immediately tells us that y prime is n plus s cn x to the n plus s minus 1 summed over from n equals 0 to infinity. Y double prime is n plus s into n plus s minus 1 cn x to the n plus s minus 2 summed over from n going from 0 to infinity. And we plug those things back in the equation. So for the x square y double prime term, you get cn n plus s minus 1. X to the n plus s minus 2 would have come from the derivative, but you are multiplying this by x square, so you get this. This is what you get from the y prime. Well, you also get another term from the 3xy prime, where the power is back to n plus s because of the multiplication by the x. And y, of course, is cn x to the n plus s summed over. Now we can collect the terms together, all the terms with power x to the n plus s, that is this term, and this term can be just added together. It's very easy to see that this is n plus s whole square plus twice n plus s, the minus 1 into n plus s cancelling with the 3 n plus s here, plus 1 coming from this with a cn overall factor. So this is just cn into n plus s plus 1 whole square x to the n plus s. And this is just cn n plus s to the power n plus s minus 1. This whole power series has to be 0. Now, in order to handle a power series, what we need to do is ensure that all the terms have the same power. That is, I need to raise the power here to n plus s. That is, increase n to n plus 1. And that's easily done. The first term is simply what you had. I had missed out the x to the n plus s here. The second term now proudly has an x to the n plus s. But the cn has become cn plus 1, the n plus s has become n plus s plus 1. But to keep track of this, the limit has to change. After all, see that here you started with a C0. The new series is the same series, you have just rewritten it in a different way. So it also has to start at C0. So since it's cn plus 1 here, n has to start at minus 1. The upper limit would also have to come down by 1, but since it's infinity, it doesn't really matter. Now we can combine these two power series together, because now you have the same power in both. Combining the two terms gives you this. But in addition, you have one extra term here which comes in from the fact that n equal to minus 1 is there here. There is no n equal to minus 1 term in this. So you have to write the n equal to minus 1 term from this separately. That of course is nothing but s times c0 times x to the s minus 1. In order that this power series vanishes identically, every power must have 0 coefficient. X to the s minus 1 is a term which only has s0, and this is what gives rise to the so-called indicial equation. So, the indicial equation clearly tells you that s must be 0, and for all of these brackets to vanish, you must have a recursion relation between Cn plus 1 and Cn. Of course, s we know is 0, so we just plug that in here. So for all n which are 0 or more, you have Cn plus 1 into n plus 1 is Cn into n plus 1 whole square. In other words, n plus 1 can be cancelled between the two since n is 0 or more, so there is no possibility of division by 0 here. And you will end up with this expression, the Cn plus 1 is nothing but minus n plus 1 Cn. So C2 is nothing but minus 2C1, which in turn is minus 1C0, and so on. If you just put that in, it's easy to see that Cn will be minus 1 to the n times n factorial C0. This is just the same kind of calculation. If you start with Cn, it's going to be minus n Cn minus 1 minus n into minus n minus 1 Cn minus 2 and so on all the way down to C0. You are going to get this. So we have found one solution of the Frobenius kind. In fact, a pretty simple solution. The index is even 0 here. And the solution, y of x, which we get, this is one of the two independent solutions of this equation. The other one has to have an essential singularity. Is of the form C0, which is an overall factor, times minus 1 to the n factorial, that's what each Cn has, into x to the n. So if I expand this out a bit, I get C0 times 1 minus 1 factorial into x plus 2 factorial into x square minus 3 factorial into x cube plus, and this goes on till infinity. So fine, we have a power series solution. This might surprise you a bit if you consider the fact that x equal to 0 is an irregular singular point. But let me remind you that what is forbidden at an irregular singular point is getting two solutions, both of which are free of essential singularities. Having one solution which is essential singularity free is actually nothing against the rules. The other solution in this case will have an essential singularity. But this perfectly good solution has one thing which ruins it almost completely, at least at first glance. If you try calculating the radius of convergence of this particular power series using any one of the standard methods, the ratio method works very nicely here, you will find that the radius of convergence is exactly 0. Of course, a similarity of this with the perturbation series for the quartic potential should be striking. That too had a radius of convergence of 0. Here we see explicitly a series which satisfies the differential equation, which has a radius of convergence of 0. And that means that this series converges only when x is 0. Of course, it converges there. It gives you just the value 1. But the moment you put in any value of x, no matter how small, this series, the infinite series, is going to diverge. So now this raises several questions. One of them is, we would love to say, okay, that this series is not really convergent but still is asymptotic to y of x. But the way in which we derived the series actually hinged on the fact that if you start with Cn x to n plus s and differentiate this term by term, you are going to get the derivative of y, and differentiate that term by term again, you are going to get y double prime. This may sound rather obvious for a finite sum, but for an infinite series, that whole step works only if the series converges. And the proof of that actually is not quite trivial. It's a proof you will find in any complex analysis text, but it's really a rather non-trivial statement that you can differentiate an infinite series term by term, and if the original series converges, the term by term differential series, which is a new series, also converges. And more than that, it converges to the derivative of the function there. Is really not a trivial thing. It takes quite a lot of effort to prove. And it hinges on the fact that the series that we started out with is a convergent series. Here, after all this calculation, we have found a series which apparently satisfies my differential equation. But the steps that we took in order to find our series actually may not be valid, because our series to begin with was not a convergent one. So, before we start to say that the series that we have found, even if it's divergent, is actually asymptotic to a solution, what we need to show, using perhaps an independent method, that the derivatives of y at x equal to 0 are actually what the series is really predicting for me. If that happens, and if you can find out all the derivatives, then, as we had discussed a while ago, the corresponding Taylor series, even if it did not converge, would be asymptotic to the solution. Let me remind you that the point I'm trying to make here is the power series method apparently gives us the series, but its validity hinges really on the series having converged. So even though we have found a series, at this stage we are not really very sure whether it really is the actual series. But we can find that out. And one of the reasons why I'm paying so much attention to this particular problem is that later on, when we deal with the perturbation series in quantum mechanics, the trick that we are going to use to show that the perturbation series is asymptotic to the actual values of the energy or the wave function is essentially the same as the one that we are using here. I should not really be calling it a trick. Trick sounds like we are actually doing something illegitimate. We are not. We are going to just use the equation directly, this equation that you can see here, to find out the derivatives. So let's see how that works out. So this is the second tack that we are using. The first thing you realize is that because x equal to 0 is a singular point, and that happens at all singular points, the derivative and the value of the function are not really independent of each other. After all, for a second order differential equation, the equation should usually be able to give you the second order derivative directly from the equation itself, given y and y prime. But here, at x equal to 0, this equation is really not second order. This term has actually dropped out. And at x equal to 0, what you get is y prime into 1 plus y equals 0. Which means that at x equal to 0, the initial condition at the singular point is y prime equal to minus y. This is valid as long as y double prime has to stay finite, so that this term x square y double prime vanishes. Okay, then if you take y0 to be 1, which you can always do, after all changing y0 simply means taking c0 to be anything other than 1. That is, it's an overall constant multiplying my solution. But if you take y0 to be 1, this restriction tells you that y prime 0 has to be equal to minus 1. The derivative here at the singular point is constrained by the value of the function itself. Okay, but what about y double prime? In order to find out all the derivatives, we would actually rely on the fact that the second order differential equation will give you the second order derivative. But here, at x equal to 0, this term just drops out. So the second order derivative does not come from the equation directly. But let's not be daunted by that. Let's say that if this equation is valid at all x, of course not only at x equal to 0, then you can differentiate both sides of this and end up with 0, because the right hand side of course differentiates to 0. So differentiating the equation gives us this result. X square y triple prime, this is from x square y double prime being differentiated, but you get one more term, 2x y double prime, plus 1 plus 3x y double prime, plus 3 into y prime, plus y prime from here. This whole thing equals 0. Collecting terms together, this gives you x square y triple prime plus 1 plus 5x y double prime plus 4y prime has to be 0. This is simply a consequence of the original differential equation. If that has to work everywhere, the third derivative has to obey a third order differential equation given like this. But once again, this really is not an equation for the third derivative because at x equal to 0 at least, this third derivative term drops out. What doesn't drop out is y double prime. What you get is at x equal to 0, y double prime is minus 4 times y prime. So it's plus 4. That's a mistake here. It should be plus 4. Minus 4 times y prime at 0. Well, you can continue. X squared, fourth derivative of y, plus 2x times y third derivative, plus 1 plus 5x y triple derivative, plus 5 into y double derivative, plus 4y double derivative equals 0. This is what you get when you collect terms together. And now, y triple prime plus 9y double prime must vanish at x equal to 0. So at x equal to 0, y triple prime is given by minus 36. The mistake that I have here was carried over from the mistake at this stage. Now that we have corrected this should be minus 36. Okay, you can keep on doing this step by step. But we can actually do it in one go. If you just start with the original differential equation and differentiate this p times with respect to x and use Leibniz formula for successive differentiation of a product, the work is really not very difficult. You have x square y double prime that gives you y square y p plus 2th derivative. This, of course, is a notation which holds for p plus 2th derivative. You should have gathered this by now. I have used this before, perhaps without explaining. Then you have p times derivative of this once and derivative of this 1 times less. So 2px y p plus 1. One more term comes in from x square y double prime by pth derivative, that's p into p minus 1 by 2. P choose 2. Times the second derivative of x square, which is of course just 2. And the p minus 2th derivative of y double prime, which is just y of p. Because there are no further derivatives of x square, this process stops here. Similarly, with 1 plus 3x y prime, you actually get two terms. One where you differentiate y p times and this not at all. The second when you differentiate this once and this p minus 1 times to get yp, and that's multiplied by p choose 1. And finally, y of course gives you y of p. Here, since y double prime and y prime are actually multiplied by simple polynomials in x, which vanish after sufficiently large number of derivatives, this whole process is really not as daunting as it would have looked like. Now, at x equal to 0, things become even more simple because you can drop this term, not this one. Here you can drop the 3x. Here, you can't drop anything. So what you get ultimately is collecting all terms together. You get p into p minus 1 plus 3p from here plus 1. This is y at p of 0 plus just yp plus 1 term at 0. This is the only connection that you get. It simplifies very simply to yp plus 1 at 0. The p plus 1th derivative at 0 is related to the pth derivative by this simple rule. You have to multiply by minus p plus 1 whole square. And it's very easy to solve this explicitly. This just tells you that the pth derivative at 0 is nothing but minus 1 raised to the power p times p factorial squared y0. This is very, very easy to work out. And therefore, y of x is nothing but y of 0, which remember is our original c0. We could have just taken that to be 1. In fact, we did take that to be 1 when we worked these things out. And these are just what the derivatives but if you wrote down the Taylor series, you would write minus 1 to the n factorial square by n factorial x to the n. And actually I should not write yx equals this because this does not converge as we have just seen. But this side is the Taylor series for y of x. And as we had just argued a while ago, if all the derivatives exist, and in this case they do, y of x has to be asymptotic to the Taylor series. So derivatives that we had obtained here are exactly the same as we had obtained by the power series method. So here we calculated the derivatives explicitly at x equal to 0 from the equation itself and plugged that back and wrote down the Taylor series. But these are exactly the same as what we would have gotten from the power series method. So although the basic steps in the power series method, term by term differentiation of an infinite series, may not have been legitimate, at the end of the day, they did give us the right answer. Y of x expanded as a series does come out to be this. Of course, the series does not converge, but is still the asymptotic series to this. Our solution then is a genuine asymptotic series. Not only that, we can actually also sum it up in a way. In order to sum this up, all you have to do is realize the following. N factorial has a very simple integral representation. By the way, this series, which we have written down here without the y0 term, which is just an overall constant, actually is so important that it merits a name of its own. It's called the Stieltjes series. I'm pretty sure I'm mispronouncing the name, but let's call this Stieltjes. I'm pretty sure it's something like Stieltjes. But anyway, here what you do is write the n factorial in terms of this integral, which is a pretty standard result. Now we carry out a step which is perfectly legitimate. Minus x to the n here is a constant, so we can just move it inside the integral. And so you are ending up with an integral of e to the minus t times minus xt raised to the power n. Integral, of course, from 0 to infinity, and then you have to sum this up from n equals 0 to infinity. Note that here you are doing the integral first and then summing up. In the next step, I'm going to do something which is not as legitimate, in fact rather dicey. I'm going to say that let's try doing the sum first and then do the integral. Now, interchanging summation and integration works fine for finite series or finite sums, or if a series is convergent, you can then still do it, at least if it's absolutely convergent. But here we are doing this under rather suspicious circumstances. Well, accepting that, let's do it anyway. We have interchanged the sum and the integral here, and because this is a bit suspect, I have written this part in red just to draw your attention to that. Well, next part, we have minus xt to the power n, which is going to play a role in our next slightly illegitimate step. I'm going to sum up n going from 0 to infinity minus xt to the power n. The e to the minus t, of course, is a constant as far as the sum is concerned. It will come out of it and get a very standard result. This is an infinite geometric series which adds up to 1 over 1 plus xt. We just plug that in. Now this gives us an integral which has a special name. It's called the Stieltjes integral. By the way, this Stieltjes is the same Stieltjes who had given us a theory of integration, the Riemann-Stieltjes integral. But when we say Stieltjes integral in particular, we mean this particular integral. Note that the 1 plus xt has also been written in red here. This is to signify that there is something illegitimate, at least at this stage, about the summation of minus xt to the n, which gave you this. And it's pretty easy to see why this is really not a perfectly legitimate thing to do. This infinite GP series does sum up to 1 by 1 plus xt, provided xt has a magnitude smaller than 1. Now x is a positive number here, at least in this calculation, but t note is any number which goes from 0 to infinity, which means xt will be smaller than 1 over a range. In fact, from 0 up to 1 by x for this integral, xt is going to be smaller than 1. But when t goes beyond that, all the way up to infinity, xt is actually a lot bigger than 1. So here we wrote this sum as 1 over 1 plus xt, which frankly is not quite correct. But let me point out that the result that we have obtained here, this Stieltjes integral, is actually perfectly well defined. It exists and it defines an analytic function of x for all positive x. The fact that it exists is a very, very simple thing to prove. After all, since x is positive and t runs from 0 to infinity, it's obviously positive. This xt in the denominator is always positive. So the denominator here is always larger than 1. So this integral, no matter what the value of x is actually bounded above by e to the minus t dt's integral. If you just change this denominator here to 1, you are bound to get something which is larger. And this integral we all know is simply 1. So whatever this integral is for whatever value of x, it has to be a finite value. At least as long as x is positive. For negative x, of course, there will be a pole at minus 1 by x, which now is a positive value. So it's a pole within your range of integration. So it might lead to a trouble there. But right now, as far as x is positive, this is a perfectly well-defined integral, whose value can be found out in a multitude of different ways, including numerical integration. You could just use a computer and call up a standard integration routine, and it will give you the value for various different values of x. By the way, this integral actually is a solution to my differential equation. To see that, let's define this as s of x. When I write s of x, I mean the integral. Later on, I'm going to write sj of x, which will essentially talk about the partial sums of the Stieltjes series. But now, s of x is given by this integral. S prime x, derivative with respect to x, is pretty straightforward. You have to differentiate this partially with respect to x to get that. And that gives you simply 1 plus xt whole square with a minus sign and an additional t which comes in because you're differentiating xt with respect to x. S double prime, very simple, very straightforward. This 2 gives you a minus 2. With a minus, this gives you a plus, and another t comes in, and therefore you get 2t squared to the minus t by 1 plus xt whole cube. Now, if you take this and plug this in my differential equation, this s and the s prime and s double prime which we have just calculated, we get this rather daunting looking expression. It takes a bit of effort to collect all these terms together, not too much, especially if you know the answer, so I will leave that as an exercise for you, to see that if you collect all the integrands together, what you get is actually a total derivative, ddt of this quantity, t by 1 plus xt whole square e to the minus t. Now, when you integrate this from 0 to infinity, you are simply going to get the value of this at infinity minus the value of this at 0. And you should notice that at both the upper and the lower limit, this term vanishes. So this integral is of course 0. So we see that our s of x, defined by this Stieltjes integral which does converge for all positive values of x, is a solution to x squared y double prime plus 1 plus 3x y prime x plus y equals 0, our original differential equation. So, while the power series that we worked out using the power series method was not convergent, we did figure out that it's asymptotic to one solution, and the solution can be written down in a slightly dubious manner because of these two illegitimate steps that we carried out here, exchanging the integral and the sum first and then summing up an infinite GP series even though the ratio term was actually more than 1 or could be more than 1 over some range. But what we have obtained after all that is a perfectly legitimate well-defined function of x, in fact an analytic smooth function of x, which does satisfy my differential equation. So the Stieltjes integral does satisfy the ODE, but we still might have lingering doubts. We know that the Stieltjes series is actually asymptotic to a solution of the ordinary differential equation. We also know that the Stieltjes series gave rise to the Stieltjes integral, which is a solution to the differential equation. But because of the two dubious steps that we carried out earlier, it could be legitimate to doubt whether the Stieltjes series really is asymptotic to the Stieltjes integral or not. But once we have the form for the Stieltjes integral, it's actually pretty easy to show that the Stieltjes series is asymptotic to it. In order to show that, we need a very, very simple result, which is the following. If you take any negative power of 1 plus xt, multiply that by e to the minus t dx, and integrate from 0 to infinity, you can actually carry out an integration by parts, using this as a function to be integrated and this as a function to be differentiated. That is, this is my so-called first function and this is the second function here. So you end up with one term, the integrated out term, where you integrate to the minus t to get minus e to the minus t, 1 plus x e to the minus n, 0 to infinity. And in the second term, you subtract from it minus e to the minus t times the derivative of 1 plus xt to the minus n, which is minus nx into 1 plus xt to the power minus n plus minus 1. Minus nx, note, you are differentiating with respect to t here, and x is the parameter which is treated as a constant. So, because it's xt here, you will get an extra x. And collecting these terms together, you end up with this very simple lemma that this integral is actually 1 that comes out from this term. The upper limit gives you 0, the lower limit actually gives you minus 1, but you are subtracting the lower limit, so there is plus 1. The 3 minuses here give you an overall minus, nx, the constant comes out, 0 to infinity. Same kind of integral except that minus n has been replaced by minus n minus 1. So integration of parts allows you to connect an integral for minus n here to an integral with minus n plus 1. And we can just use that starting with n equal to 1, which is of course our Stieltjes integral. 0 to infinity 1 plus x to the minus 1 into the minus x dt according to this integral is just 1 minus 1x into 1 plus x to the x e to the minus 2 e to the minus 2. Integrated, you can do it again. You can write x with this integral as 1 minus twice x, n is 2 here, with 1 plus xt to the minus 3 e to the minus t dt. That gives you 1 minus x plus 2x square into this integral, which can be broken up further using that. And you can easily see that you can keep on doing this over and over again, and you get 1 minus x plus 2x square minus 3 factorial x cube times this integral, which is 1 minus 4x into something like that. And as you keep on doing this, up to capital N terms, you will get small n running from 0 to capital N, minus 1 to the n, small n factorial x to the n, plus an additional term which will come from an integral like this, which we have still not worked out. Notice that there is no approximation here. This is an exact result. This additional piece, the remainder piece, is what we need to focus on. This epsilon x is nothing but the last term that you had was minus 1 to the n, capital N, n factorial x to the power capital N, times a minus n plus 1 x, 0 to infinity integral and so on. So if you collect them all together, you get minus 1 to the power n plus 1. You already had a minus 1 to the n outside, one more minus sign. You had an n factorial outside, multiply by n plus 1 gives you n plus 1 factorial, x to the n plus 1. 0 to infinity, 1 plus xt to the power minus n minus 2 e to the minus t dt. That's just the term that we still left as an integral, did not proceed one more step with it. So this is the additional remainder piece. Now, if you are going to claim that the Stieltjes sum 0 to infinity minus 1 to the n n factorial x to the n is asymptotic to my Stieltjes integral, you have to show that this remainder term actually is negligible compared to the last term that you have used here. That is x to the power capital N. Well, note that if you take the magnitude of this remainder term, this of course goes away. You get n plus 1 factorial x to n plus 1 times this integral, which by the same argument that we used to justify that the Stieltjes integral exists, is actually bounded by e to the minus t dt's integral from 0 to infinity, that is bounded by 1. So epsilon nx is less than n plus 1 factorial x to n plus 1. Less than because this integral is actually less than 1. And this, remember, is negligible compared to x to the n. As we have already said before, higher powers are negligible compared to lower powers as x tends to 0 plus. Which is all you need to establish that the Stieltjes series is actually asymptotic to the Stieltjes integral. So all those dubious steps that we carried out still ends up giving me a correct asymptotic answer. The Stieltjes integral does exist. The Stieltjes series is asymptotic to it. That is, at any given stage, the remainder term that you have is negligible compared to the last term that you just are ignoring. So at long last, we have this result that the Stieltjes series is really asymptotic to the Stieltjes integral. Now you might still ask a question. What is the use of the Stieltjes series? The Stieltjes integral, I can understand, does satisfy my differential equation, is a legitimate function of x, which can be worked out, say, numerically. But is the Stieltjes series at all of any use? The answer? Well, let's check that. The value for the Stieltjes integral for x equal to 0.1, a reasonably small value of x, is given by this quantity, which can be worked out very easily. I just asked Wolfram alpha for the answer, and it told me that the answer, at least approximately correct answer to 6 decimal places, is 0.9115633. Let's now try to figure out what the partial series sums for the Stieltjes series will give us. We already know that the series is divergent, so if we try to push it too far, the sum has to become larger and larger without bounds. But let's start and take a look at the first few terms. This is your Stieltjes series sum to capital N terms. You are ending at minus 1 to the n factorial x to the n. Okay, this is really n plus 1 terms, but frankly that's not really a matter to quibble about. What about S0 0.1? That's just the first term, 1 alone. And you might even argue that 1 is not too bad an approximation for 0.915633. But that is really pushing it too far. But what about S1? S1 is straightforward. It's 1 minus 1 factorial times 0.1. So 0.9. Not bad actually. With just 2 terms, you have got 1 decimal point accuracy. Well, what about 3 terms up to S2? Well, that's basically 0.9 S1, to which you are going to add 2 factorial times 0.01, so 0.92. Not really bad at all. Well, what about S3? From 0.92, sum up to this, you have to subtract 3 factorial times S cube. Minus 6 into 0.001, that is minus 0.006 has to be subtracted. You get 0.914. S4, you get 4 factorial times 10 to the minus 4 here, and that gives you 0.9164. By the time, you should realize that we are getting pretty close to the supposed exact value. S5, 0.9152. These calculations can be easily done by hand. You don't even need a calculator for this. especially because we have chosen a very simple value for x where the calculation is really easy. The higher powers of x just add one more decimal place. S6 gives you 0.91592, S7 915416. Let me remind you once again, the actual value is 915633. And by the way, let me just point out something which you may have already noticed. 1 was actually more than the exact value, S0. S1 is 0.9, is smaller. S2 is larger. S3 is smaller. S4 is larger. S5 is smaller. S6 is larger. S7 is smaller. So these are really alternating between being larger and smaller than the actual value. And so you know that the actual value is somewhere in between these two, which is actually quite tight bound. The fact that you know it's in between tells you that the first 3 decimal places here are actually quite correct. So with 6 terms only for a sum, you've got the first 3 decimal places. If you start with standard convergence series with a small, say x equal to 0.1 for 1 by 1 plus x, the sum actually does not converge that rapidly. S8, well, even closer and an overestimate. S9, an underestimate. But notice, S9 is lower than S8. S10 is back at S8 because what you add up here is 10 factorial into 10 to the minus 10, which is exactly the same as 9 factorial into 10 to the minus 9, which is subtracted from S8 here. So S10 will be the same as S8. And now things really start getting worse. Earlier, the things that you're adding or subtracting became smaller and smaller, but now at this stage, the 2 terms that you subtracted to get S9 and added to get S10 are actually exactly equal. After that, the terms become bigger and bigger. So the sandwiching effect is still there because these terms alternate. It's easy to see the successive sums will be either smaller than or larger than the sum. But now the thing goes wider and wider apart. But notice that before this widening happens, you already have a very, very good estimate for the actual sum. It's between 0.9158 and 0.9154. Well, I would be tempted to use the average here and say it's 0.9156, which actually is 4-figure accurate. But this is a very tight bound to put your actual series in. Here, of course, the series was alternating, so successive partial sums actually underestimated or overestimated, respectively, the actual sum. And a relatively small number of terms actually gave you a pretty good estimate, and the smallest term in terms of size, which is reached at the S9, the 9th term, or the 10th term, they are actually the same size. But they are the smallest ones. After that, things get worse. But the smallest terms actually give you the best possible estimate from a direct summation. I would urge you to try to sum up 1 by 1 plus x's infinite series for x equal to 0.1 and see how many terms it takes for you to get 3 decimal places accuracy. Here you got it almost after 4 or 5 terms. And this is actually typical. Asymptotic series which are divergent actually work better as far as speed of getting close to the actual answer is concerned, typically, than asymptotic series which are convergent or just ordinary convergent series. And you don't really have to stop here. There are things called convergence accelerating transforms which can be used to improve the rate at which you approach the final result and also get more and more decimal places. And convergence accelerating transforms work for both convergent series and asymptotic series, that is asymptotic divergent series. And it's a matter of experience that for most cases, they work faster for the asymptotic divergent series than they do for convergent series. So divergent series actually help you to get values, real numbers calculated for quote-unquote sums faster than convergent series do. Very, very often. Not always, but the general rule is asymptotic divergent series give you the value with less effort. So the fact that the perturbation series is an asymptotic series is not something which is to be sort of thought of as a handicap. It's actually an advantage. Now we will turn to perturbation series in the next part of these lecture series. But before we go there, just for the sake of completeness, let me mention one thing. The asymptotic series that we talked about were series essentially like the Taylor series. They were power series in x minus x0, except that the series could have diverged. It could also have non-integral powers. For example, you could have an x minus x0 to the power alpha n with a positive alpha, n running from 0 to infinity, but alpha may be fractional as x goes to x0. Now, you say that this is asymptotic if the definition is very similar. If the difference between y of x, the function, and the partial sum up to n terms is negligible compared to the last term that you are taking. That is, x minus x0 to the power alpha n. Well, another kind of asymptotic series which is actually very, very important, and we have already seen example of that. The Stirling formula is an example of the beginning of an asymptotic series. For x0 equals infinity, we actually have negative powers. So, an x to the minus alpha n summed up over all n is asymptotic to y of x. If once again the same thing really happens, if you do a partial sum and take it away from y of x, the difference is negligible compared to the last term that you have retained, x to the minus alpha capital N in this case. If that happens, you say the series is asymptotic at infinity. Note that for the kind of power series that we talked about earlier, as x goes to x0, x minus x0 to the power 0 dominates x minus x0 to the power 1. This is negligible compared to this. Negligible not just in the standard English language sense of the word, but also in the strict mathematical definition of negligible that we introduced here. X minus x0 whole square is negligible compared to this. X minus x0 whole cube is negligible compared to this. So when you're expanding out a function in an asymptotic series in powers of x minus x0, you are actually doing this in a sequence of functions of x minus x0 to the power something, which are successively negligible in comparison to the previous ones. And that is what you have done for all of these cases as well. X minus x0 to the power alpha into 0, x minus x0 to the power alpha into 1, x minus x0 to the power alpha into 2, and so on. For positive alpha, these are successively negligible functions as x approaches x0. As far as x going to infinity is concerned, x to the minus alpha, x to the minus 2 alpha, x to the minus 3 alpha. In this sequence, the successive terms actually become negligible compared to the previous ones in the limit x goes to infinity, which is where this is asymptotic. So in general, we can actually also talk about a more general situation. Instead of asymptotic series with powers of x, we could talk of asymptotic series with base functions of x, phi 0, phi 1, phi 2, phi 3, and so on, where the basic condition is phi 1 is negligible compared to phi 0, phi 2 is negligible compared to that, phi 3 is negligible compared to that, and so on as x goes to x0. Then we can write yx as sum of am phi m for m going from 0 to infinity, and that would also be an asymptotic expansion with this particular basis series. Unless otherwise mentioned, we would typically mean the standard power series kind of expansion when we say yx is asymptotic to a series, but these are also other possibilities. And depending on your application, they are pretty useful from time to time. What you are claiming is yx is asymptotic to am phi to the m running from 0 to infinity, if for all n, the difference between yx and the partial sum to n terms is negligible compared to phi capital N. The pattern is the same everywhere. For the time being, this is all we have to say about asymptotic series. This is actually a small part of the entire wealth of information which asymptotic series actually has. For example, the differential equation that we talked about, we have only found one of its independent solutions in the form of the Stieltjes integral. Asymptotic techniques actually tell us how to find the second solution as well and find out how it behaves close to x going to 0. But for the time being, we are not going to go into all that for the simple reason that our main aim here is to talk about perturbation series in quantum mechanics. Whatever asymptotic methods we have talked about in this part of the lecture is going to stand us in good stead when we talk about the asymptotic nature of the perturbation series in quantum mechanics. That will be in the next part.